Greetings everyone. Okay, so here is a tutorial about antiderivatives using a substitution. The relationship that I have shown here is generally what we're working towards, but we'll talk more about that in a minute. Let's talk some other issues first. Remember, substitution is a method for finding an antiderivative that's not necessarily the first thing you try until you gain a lot of experience and you know that it's going to be obvious you're going to need a substitution right away. But initially, when you're first learning how to find an antiderivative, the first thing you want to do is try to use recognition. You look at the integrand, the function you're trying to find the antiderivative of, and ask yourself, do I recognize this as the derivative of some function that I know? Since we know how to take a lot of derivatives, this is going to happen on occasion, and so we might just automatically recognize what the antiderivative should be. And so recognition is what you're trying to do usually first. The second thing is, can you reverse the power rule? We know how to do the power rule for taking a derivative, so do I recognize the expression as constant times x to some power, and maybe some sums or differences in there, and then I can reverse that power rule and end up with the antiderivative. So if you try those things first, you may not have to use a U substitution. Some examples of those here are like this. So the first one here, we should recognize that that 1 over x is the derivative of the natural log function. Specifically, it's the derivative of the natural log of the absolute value of x, if we want to be most general about it. And then, of course, we're going to need our plus c. So that's an example of using recognition for finding the antiderivative. We know 1 over x is the derivative of a function we're familiar with. Therefore, we can find the most general antiderivative immediately. In example 2 here, we can reverse the power rule. So in working this out, remember, we're going to add 1 to the exponent that we have. So negative 4 plus 1 is negative 3. And then, looks terrible, then I need to divide by that new exponent. And then, of course, add your constant. Keep in mind with the negative exponent that this could be rewritten as 1 over negative 3x cubed, and of course plus a constant. And you could check these results by actually taking the derivatives and making sure that things work out the way they're supposed to. So those are the things you try first before you ever really consider substitution, until you're really good at this stuff, and then you can recognize things fairly quickly. Alright, so let's try something else here. There is something that you should never do. Sorry, just making sure I'm on the right page. There's something you should never do in looking to take an antiderivative. You should never separate multiplication or division of functions, except for constants. Constants are not what we're referring to here. What happens occasionally is that students will see two functions being multiplied together, and they will think that they just take the antiderivative of each factor and then multiply the results together, they'll get the antiderivative. That doesn't work, okay, in general. So that's not a technique we're going to try, or we want to try. So an example of what you should not try for a couple different processes of finding antiderivatives are these two examples right here. What you do not want to do is you do not want to try to take the antiderivative of the x term here and then take the antiderivative of this, even though you can't at the AB calculus level, AP calculus AB. We will be able to handle that with some BC techniques, but you don't want to try to take the antiderivatives of these terms separately and then multiply the result. That is not a process that's going to give you the correct answer. This example actually here, we'll tackle that a little bit later, but this one is an example where we will want to use a U substitution, or rather substitution, in order to work this out. The second example here on the page is also one that you don't want to do the numerator, the antiderivative of each term in the numerator separately, using, of course, reversing the power rule, and then doing that to the denominator, and then just taking the quotient, thinking that that's going to work. What you'd want to do for this example here is you want to do the algebra simplification first. So x squared over x gives me x. 2x over x is 2, so minus 2, and then plus 1 over x dx. And then once I do that algebraic simplification, then I can go through and take antiderivatives. I can find the antiderivative of x using reversing the power rule, the antiderivative of 2. You should recognize that, the antiderivative of 1 over x. And then, of course, plus a constant. So you can work this one out without a substitution. But what you cannot do is do the numerator, the antiderivative of the numerator, and the antiderivative of the denominator, and then take their quotient as a correct result. So don't do that. If you ever try that, most of the time you're going to be wrong. And I say most because I'm sure there are some isolated examples where that accidentally works, but it's not a technique that you want to use in general. So never try the separations. All right. So the process of doing a substitution to work out an antiderivative is based off of reversing the chain rule. So if you recall from the chain rule, the derivative with respect to x of the composite function f of g of x is f prime of g of x times g prime of x. So if I start at the end result over here and then want to find the antiderivative of that, we know just by inspection here, by recognition, that the antiderivative has to be f of g of x, of course, plus a constant. And the reason why we recognize that is because we're just going backwards from here, we took the derivative to get this result in the first place, so we're now going backwards in finding the antiderivative. To be most general, we of course get the whole family of solution curves plus c. But really the question becomes, I think a little bit, becomes how exactly would we do this when we don't recognize and don't know ahead of time what the result is. We can actually do the substitution here and see how things work out. So if for a moment I let u equal g of x, then du is going to be equal to g prime of x dx. So up here in my expression, we can see that I have g prime of x dx over here, and so I can replace all of that with my du, and then I have f prime of g of x, so I can plug a u in here. And so this whole expression, let me get rid of that arrow, I don't like that there. This whole expression can be rewritten as the indefinite integral of f prime of u du. So again, we're just making a substitution here, and so what we see is u is in place of g of x, that's why that's here, and du over here is in place of the g prime of x dx. And then we can take the antiderivative of f prime of u du, that's just f of u, of course plus a constant. But we remember that u is equal to g of x, and so when I replace u with g of x, I end up right back to where I started up here in yellow. And so that's the idea behind the process. We're going to find some function, typically a quote-unquote inner function, where when we take the derivative of that inner function is a factor. Okay, so by letting u be equal to g of x, when I took the derivative, g prime was a factor of the integrand, and therefore the substitution is appropriate. We can make that substitution and then work for the answer. Incidentally, this last, the second to last step that I did over here, when I looked at this result and got this, that was by recognition. We know the antiderivative of f prime is f. And so I'm still using that foundational understanding of I'm trying to recognize the integrand as the derivative of some known function, and I recognize f prime as the derivative of f. So that's still a part of what we are doing. So let's take a look at the example we said we could use a substitution on earlier. So just to get this practice in your mind, you should try to recognize this function as the derivative of some other function. Believe it or not, with enough experience, you probably could recognize this as the derivative of some function, but that usually takes lots of practice with this stuff and lots of experience. And so I wouldn't expect you to recognize this here. So I would expect you to do a substitution. Reversing the power rule here is in this form not yet appropriate, and so our next choice to try to figure out something to do is a substitution. And so we typically, as we've mentioned before, let u equal something. The choice of the letter u is really arbitrary. We could use a different letter provided it's not already used in some form or context of the problem as defined as something else. It's a dummy variable, so we just use whatever we want. So my goal is to find an expression for u that is an inner function, so that when I take the derivative of that inner function, I have at least a constant multiple of its derivative as a factor. If that was a little confusing in the words, I'll show you what I mean by that. All right, my inner function that I'm going to choose is 25 minus x squared. You'll start to recognize as you practice this what good choices of u happen to be with experience. But then you might fail sometimes. You choose a value of u that doesn't quite work the way it's supposed to, so you choose something else and then try it again. So with my experience, I'm going to try that as my expression of u. And by the way, there are more than one potential choices that we could choose as well, in general. Not always for every problem, but sometimes more than one choice of u would be acceptable. All right, so then we want to compute du. Derivative of 25 is 0. Derivative of negative x squared is negative 2x dx. Put a little differential there. Now, if you notice in the problem as it's stated right now, we have x and dx, so this part is there. What we don't have is that constant negative 2. So I need to get rid of that from the at least I want to get rid of that from the expression in the x dx side over here. So I'm going to multiply by negative 1/2 on both sides so that I'm left with negative 1/2 du equal to x dx. So now in place of the x dx, I'm going to put in place the negative 1/2 du. And then from there, I just need to substitute for 25 minus x squared u, and we'll see if we can work this out. So I paused the video for a moment so that I can save some time. So I made the replacements. In place of the x dx, I put in the negative 1/2 du, and I put the negative 1/2 using the constant multiple rule for integrals here as a multiplier outside the integral symbol. You can put it on the inside, it's not incorrect, but I just like to put it on the outside. And so the x dx replaced by negative 1/2 du. And then under the square root, we replace that 25 minus x squared with a u. And so you should be thinking about this in terms of reversing the power rule. So let's rewrite u with a fractional power 1/2. And then let's work the antiderivative out using reversing the power rule. Constant multiple rule brings the negative 1/2 along for the ride. Reversing the power rule, we're going to add 1 to 1/2 to get 3/2, and then we're going to divide by 3/2, which is the same as multiplying by 2/3. And so we get 2/3 times u to the 3/2, and then of course we're looking for the most general, so squeeze in a plus c. And we can do a little bit of algebraic simplification here. The 2's are going to cancel, and we're going to be left with a negative 1/3. And then we're going to replace u back with the original original expression in terms of x, 25 minus x squared, all of that quantity to the 3/2 power, and then of course plus c. You can check this by taking the derivative, and if you do so properly and maybe have to manipulate it a little algebraically, you can get this result or get the integrand back. So there's an example of doing a substitution. So here's another example. What I would like you to do is to pause the video and go try this. The reason why you should try this is you may be successful and realize that you have a better understanding than you thought you did, and then you may not be successful and you get a sense of where you're having trouble, so that when you watch me go through the explanation, you actually can then start to understand the particulars of where you go wrong, and not just, blindly listen and think you understand everything. It's much better if you practice it first. So pause the video, come back, and we'll see what to do here. So hopefully you had some success. Hopefully you got all the way, and if you didn't get all the way, then hopefully you got at least started a little bit and have a sense of the things you need to improve upon. So with something like this, we have some choice, but not a lot of choice of what we could choose for u. Now, since I created the problem, I know what to choose right away, but some of you might have tried the sine function, and just doing this mentally, the derivative of sine, this is sine of the natural log of x, I know that, but just thinking of the outer part of that, the derivative of sine is cosine, and so that's not a good choice here, because I don't see cosine as a factor anywhere, so I wouldn't want to choose sine of the natural log of x as my expression. How about the over x part? Well, I can't let u equal x because I don't have x as a factor. I have 1 over x. We're dividing by x. So I could let u equal 1 over x and see if that works. But the derivative of that is negative 1 over x squared. And again, just trying that mentally, I don't see how that is going to work here. I don't think it really does. So that's not a good choice. The last thing we could try here is our natural log function. So if I let u equal the natural log of x, then du will be 1 over x dx. That should look familiar. I have dx over x in my expression already. So I can replace that dx over x part with du, and then the expression that I end up with here is going to be the indefinite integral of just sine of u du. Now we should recognize that sine, or rather the derivative of cosine is negative sine, so this is going to have to be, we're missing the negative sign, so we're going to need a negative cosine of u plus a constant, because if I take the derivative of negative cosine, I get positive sine u times u prime plus c. So now, replacing u with the natural log function, we get negative cosine natural log of x plus c. Let's just check the work on this one just to illustrate why that might be helpful and to have a better understanding of the process, hopefully, and why it works. I'll put the plus c in there even though we know the derivative of the constant is 0. So negative, if I use the constant multiple rule, I'll leave that aside for a moment. Derivative of cosine is negative sine times the inner, or evaluated rather at the inner function, times the derivative of the inner function. Derivative of natural log of x is 1 over x. So it looks like I get the opposite of sine of the natural log of x times 1 over x. Again, the derivative of c is 0, so I don't care about that. Well, the negatives cancel with each other in the multiplication, and I can rewrite this using a little bit of fraction multiplication, rewrite this as sine of the natural log of x over x, which is exactly the same as what we have in our integrand up here. That's a terrible looking oval. So we did it right. We have the right answer. So here's another example to try. Again, please go pause the video. See if you can do this one. Hopefully by now you're starting to see the patterns a little bit and becoming more proficient at making the substitutions, and you can get a correct answer without my help. Hopefully you're back now and you've had some success here. There might be a couple different choices here that work, and there might be some bad choices in this example here. So you might have run into some problems. Let me give you an example of a choice that isn't going to work very well, at least not the first time through. We can let u equal x squared, and if I do that, I get du is equal to 2x dx. If you did this, there's nothing wrong with this step so far. Everything looks like it might be working out. I'll get rid of that constant, and I need to replace the x dx with a 1/2 du, so I get a 1/2 integral sine of u cosine of u du. Now, do I know any function whose derivative is sine times cosine? You might, but it might not be obvious to a lot of people, so then for a lot of people you'd be stuck right now. How am I supposed to handle this? Well, we have a couple different options of how we can handle this. We could try another substitution with a different variable and see if we can make this work by proceeding forward. And that is possible in this example here. Or we could start over and choose a different u. I want to do both of these. Most of you probably at this step would just start over, and there's nothing wrong with that. I'm going to show you starting over, but not yet. I want to show you how we can get through this in this direction first. Incidentally, this would not have been my choice of u to start with because I see a different pattern here that I would have liked to use. I do know that sine and cosine are related to each other by derivatives. Derivative of sine is cosine. And so that gives me an opportunity here. So if I let I'm sorry, I can't use u again. If I let w equal sine of u, then dw, there's a cartoon reference there that kids laugh at when I use w in the past. I don't remember it off the top of my head, but you might get it. dw is going to be cosine of u du, like this. And so I can replace this whole expression over here, cosine of u, with dw, and then I can rewrite this as 1/2, I don't want to forget the 1/2, the integral of just w dw. I can find the antiderivative of w, that's no problem. So this is going to be 1/2 from the 1/2 on the outside. Reversing the power rule here, and we get another factor of 1/2, w squared plus c. Now I just got to substitute back in a couple different things. I'm going to try to squeeze this in here. So I get 1/4 w, which was sine of u, so it's going to be sine squared u, of course, plus c. But u was x squared, so this should be 1/4 sine squared of x squared plus c. And we obtained the answer. It was maybe a little messy along the way, messier than we wanted, but we got there. As I said a moment ago, a lot of you might have just stopped and that procedure and had chosen a new value of u, and maybe got the answer in a different way, which is what we're going to do right now. But this one worked, and I am happy with that. So what about a different choice of u? What if I would have let u equal, let's let u equal, how about we let u equal sine of x squared? As I mentioned in the previous process, that derivative of sine is cosine, so maybe that holds some promise here. So if I take the derivative, or find du, I'm going to end up with cosine of x squared times 2x, don't forget the dx. Well, that looks pretty good, actually, because I do have cosine of x squared, I do have an x, and I do have a dx. I have an extra factor of 2 that I need to get rid of, but we can handle that. So I put 1/2 du here. That's going to be I'm going to rearrange this just slightly so it may look a little bit more consistent with the pattern in the example. 1/2 du is going to be x cosine x squared dx, and so all of that stuff, the x cosine squared x squared dx becomes 1/2 du. So I can rewrite my integral as 1/2 the indefinite integral. The x cosine squared x squared dx all go away. They become du. So the only thing that's left is the sine of x squared, but we called that u, so this just becomes the integral of u du, times that half, of course. So let's see, 1/2, reversing the power rule, we just did this, times half u squared plus a constant, and now half times half is 1/4. U is sine of x sine of x squared, so this is going to be sine squared of x squared, then of course plus c, and lo and behold, it's the exact same answer that we got over there. Incidentally, you could have let u equal cosine of x squared. Your answer would look different, but it would be mathematically equivalent. This video is running a bit long, so I'm not going to show you that one, but it might be worth working out on your own just to see it. the last thing I want to talk about in this video is, what about if we need to do a u substitution to a definite integral in order to work out what the value of the definite integral is? Remember, we want to use the fundamental theorem of calculus to evaluate a definite integral. So I need to find an antiderivative, if possible, of the integrand and then evaluate it at the upper and lower limits of integration and then subtract the results to get my value for the definite integral. So let's kind of run through this process a little bit here and see what happens. We've already done the definite integral version of this without the 0 and the 5 as our upper and lower limits of integration, rather lower and upper limits of integration. So let's recall what we did. We let u equal 25 minus x squared. And so then we had du is equal to negative 2x dx. And we got rid of the negative 2 on the right hand side by multiplying by negative 1/2 on both sides. We got negative 1/2 du is equal to x dx. And so when I go to rewrite my expression here in terms of u, I end up with a negative 1/2. It's going to be a definite integral, but I'm not going to put the limits of integration in there just yet. Remember, at this point we ended up having u to the 1/2 power du. Now, the reason why I don't want to put I didn't want to put the upper and lower limits of integration in there yet is because I want to remind you of what's going on here in this process. What's going on here is this. Remember, we're finding the net signed area bounded by this function on the interval 0 to 5. And so the values of 0 and 5 are x values. I don't even know if you can see what I just did. I circled those values. Only circle with a darker color here. 0 and 5 come from the x-axis. They're x values as indicated by our dx, or the fact that our expression is in terms of x. What I need over here is values in terms of u, because I'm integrating with respect to u. So I need to translate these values from being x quantities to being u quantities. And so how do I do that? Well, I have the relationship right here in front of me. This right here, this expression, is what relates x and u together. So to find my new lower limit of integration, I can plug 0 in here for x, and I calculate 25 minus 0 squared, which is 25. And so my new lower limit of integration is going to be 25. How do I get my new upper limit of integration? Similar process. Plug in the 5 over here in for x to get 25 minus 5 squared, or 25 minus 25, which is 0. So I've just used my relationship that I defined relating u to x to take the x values that were my upper and lower limits of integration and to make them now u values to be upper and lower limits of integration in my new integral, definite integral, that is now in terms of u. Some of you might be saying, but why is the lower limit greater than the upper limit? Well, that's the way it happened in the way we translated this. But we can fix that, and we can fix that by just reversing their positions, putting the 0 on the bottom of the 25. But you have to recall that to do that, I have to change the sign of the integral. And let me make some space here for this. So instead of having a negative 1/2 in front, I'll have a positive 1/2 because the switching of the upper and lower limits makes the result opposite. So now we just have to go through the process here. I still have this 1/2. Reversing the power rule as we did earlier, we're going to end up with 2/3 u to the 3/2 power. And then we need to evaluate that from 0 to 25. Now the nice thing about switching the upper and lower limits to being in terms of u, or being u values, I don't need to go back and substitute in for x at this step, or rather substitute in for u in terms of x at this step. I already have u values for my upper and lower limits, so I can just plug those in for u. So I'm going to get 1/2 of, if I plug 25 in here for u, 25 to the 3/2 power, take the square root, get 5, then raise 5 to the 3rd power to get 125. and then multiply by 2/3. I'm doing some of this mentally, but 125 times 2/3 is 250 thirds. And I'm trying to move, we're already at the 30-minute mark here. If I plug 0 in, 0 to the 3 highest power is 0 times 2/3 is 0, so this is just minus 0. And therefore, it's just half of 250 thirds, which is 125 thirds. And there's our final answer. So just make new upper and lower limits of integration using the let u statement there, relating u and x together. Plug in your upper and lower limits that were x values in for x, calculate your new upper and lower limits for your u values, and then finish the problem in terms of u, leading to a final numerical answer. All right, go study.